Alright, today we continue to talk about the Kalman filter, but it's another Kalman filter, is standard Kalman filter. But before we talking about standard Kalman filter, I want to recap the last video I mentioned about the standard Kalman filter and how we define the formula, the Kalman filter equation. It's really important for you to understand the term in the Kalman filter equation. What the F, what the R, what the Q right here, and K right here. Okay, we already know in the Kalman filter cycle, always have two states. The first one, the measurement update, and the second one, the state prediction. So in the Kalman filter equation, we get right here. You remember Q is the process noise, and the R we add right here is the measurement update. We have the measurement noise right here to update the state variable, and the covariant right here. All the formula right here is different, the one dimension, because we change to state space equation, right? That time we already solve the problem for mobile wire robot and with the linear motion. Okay, and we change this formula into we build up the model for the motion right here, and we got the f right here. You know, f is a state transition function, remember that. And we got the the noise, the measurement update right here. We got the measurement update, mean we got the Z is what? Z is mean the measurement from the sensor, and we got it, and we deploy to the we got the measurement function S right here, and we calculate the gain, common gain, and we add to the formula to get the covariant update and state variable update. Is really important for you to understand, and I also give you some example. Look at the example right here. For example, right now we're tracking another example to apply the Kalman filter. For example, we're tracking the state pedestrian. Now we're tracking the pedestrian. Okay, how objects move onto the road. For example, autonomous vehicle right here, they're tracking some object. For example, the pedestrian, they move into the vertical and horizontal as y with the different velocity vs and vy, right? And so how we know the and we have the state variable update right here with the app is, but can you guess what the app right here? App right here is, what do you mean? It's the how the matrix dimension, 4x4, 4x3, 2x4. What do you think? Just thinking. I show you right here. Your S variable is a 4. 1, 2, 3. In this column, they have 4, right? 4 items, right? So, and it's a 4 right here. So you can easily use the linear algebra. You can guess it's a 4x4, right? 4x4 times 4x1 is 4x1. The result is 4x1, right? So app right here is mean 4x4. So look at right here, you can see this one is so this correct the answer, right? And in another example right here, you're tracking the position, velocity, of acceleration of the drone. With the drone, we care about the height a lot, the dimension Z right here, and the velocity and the acceleration right here. So you continue practice to find the app right here. What the app right here? They have in this column we have a 3 item, right? So if what the app dimension right here, so we have a 3x1 right here, 3 times 1, but right here it had to be 3 times 3, right? The answer is 3 times 1 dimension, right? So, but what different right here? You remember right here the coefficient right here, you see that's they include up the acceleration. So That's remind you what we learned about the standard common filter equation. And one more thing I want to talk right here is we analyzed a little bit the constraint of the common filter equation, standard common filter equation right here. To see how it's really correct, right? The first one, if we have the perfect measurement, it means the sensor measurements are really correct, no noise, no uncertainty. It's the sensor is really good, 100% correctly the data. So what the result? So right here, R represent for the noise of the sensor. So right here is if you suppose assume is correct, so we say it's 0, and we plug back into the formula, we got a K. Again, common gain is inverse the measurement metric, right? So, and we got plug back into the formula right here. You got the update state variable as equal measurement, right? Because why? Because the measurement is perfect, it's 100% correct, the data. So the posterior state is in the measurement update is equal to measurement. Okay, we don't care about the state prediction anymore. So it's the measurement is correct, right? So in another way, if we negligible the sensor has so many error inside, and the error go to the infinity right here, and we do the same way, plug into the formula, and we got the state common gain right here is equal 0, and the update state variable equal the state prediction. Why? Because the sensor too many error and infinity, right? And we got the result posterior state measurement updates equals state prediction, right? So in general, we have the constraint right here. If we have the perfect sensor, we have the state variable equal the measurement update equal measurement. Or in another way, we have a negligible sensor. Is the sensor so bad? So we have the result of the state state of the variable equals state prediction, right? So in calculation, this common gain is always in between these two, right? It's around here. So I just want to show you how common filter equation is correct in many ways. So today we talk about the extended Kalman filter. Why is that? If you already understand the Kalman standard Kalman filter, extended Kalman filter, that's one more complete step to show. We still rely on the standard Kalman filter, but a problem right here. We show the nonlinear motion. Last time you already saw the linear motion, right? It's a linear motion. Why? Right here, linear motion robot, right? We have the model linear motion robot. So right now we show, but in the nonlinear motion, how we solve this problem? We know the robot not only move straight, okay, they had to move the circular or the curve, right? That's a nonlinear motion, right? So but we apply the Kalman filter. The Kalman filter does apply for motion measurement models are linear, and state space can be presented by the unimodal Gaussian distribution. You know that, right? So it means you have the input is the Gaussian, so the output had to be the Gaussian. That's a linearly Gaussian, right? So right here, for example, you have the prior state is a Gaussian, right? So with the mean and the covariance, but this distribution undergoes the linear motion E equal as plus B. The posterior state right here is the Gaussian too, right? It's a linear motion, linearly, right? So if the input is the Gaussian, the output has to be Gaussian, right? So right now, if the robot move different function, it means they have the non-linear motion right here. Your attention, right? So you think the result is the same thing? We get the input is the Gaussian, the output not the Gaussian anymore, right? But how to solve this problem? We want the result is had to be the Gaussian, right? To apply the Kalman filter. So look at the small part right here. We can linearly approximation for this function, right? How to do that? In small part of the function, we can linearly approximation for this function, right? We can change to the and we apply the Kalman filter. So and from that we can apply mu can transform UF to get the mu prime, and covariant. We have to apply covariant. We can use the fs. We use another function to get the covariant. Okay, another way we use linear approximation function to get the covariant update. Okay, so how to linearly approximation right here in small part of the function you can linearly approximation right here. We use Taylor series. Taylor series is a sum of infinity term, right? But for the linearly approximation we not only have two first term right here, right? And we get the function similar the y equal a s plus b. So we can apply Kalman filter, and we got the result is a Gaussian right here. Okay, that's a different step. One more step, we can use the Taylor series to get the linear approximation for nonlinear function and apply update covariant, right? So that's a different step for the extended Kalman filter. So nonlinear function can be update the mean function, right? Mu use the fs, we can upgrade mu, but covariant we cannot use fs function fs to upgrade covariant. We had to use the a linear approximation function f to update the covariant, right? Here's a function f, right? So now you how to use the linearization in the multiple dimension. So this is the Taylor series. It's a complicated. So, but we only got the two first term for the linear approximation function right here. Right here we call it Jacobian Matrix. So, expand the form Jacobian Matrix or partial derivatives. It tells you how is the component at change. We change its component. So this Jacobian, I don't want to go deeply in map right here, but I show you a very detailed example, and it help you easily understanding more than a map right here. The row correspondent to the dimension of the function f, and the column right here is related to the state variable of s, right? So this example I want to show you. In this schematic, for example, we tracking the object as a y coordinate on the object. So our state vectors s and state variable s and y right here. State variable s and y right here. we have the function our state s and y, but in the measurement right here, look, pay attention to this example, because I use this example will be deployed deeply inside the map for the next video for tracking the pedestrian, the autonomous vehicle tracking pedestrian on the road. And right here we have a function state variable s and y, but we use different sensor. We use, for example, radar sensor to measurement, and the result right here, they don't show s y, they show the z. Right here is the radius, it means the distance from robot to the object, okay, and the angle between the r and s axis, right? And they show the result right here, how to mapping from z right here to s and y. So it's important to know the using the Cartesian represent of the world, and the measurement right now, the polar representation. So but we have the relation between the Cartesian and polar coordination, right? So we have to write down the relation between the radius and angle with the s and y, right? So I will show something analyzed picture in the next video, because this example is really cool for tracking the pedestrian on the road. And after that, we so now we apply the common filter equation. We have the right now y equals z is the measurement. In the common filter, you have the arrows between the measurement and the state prediction right here. Right now we don't have the h anymore. We have the function h right here. So the measurement residual, it means errors, equation come z minus the h, right, of s, right? So and measurement covariant matrix cannot be updated the same way. It's had to be turned into the non-Gaussian distribution, and so let's calculate the linearization h, okay, and we use the h right here for update the covariant matrix. So we use the Jacobian formula. We got the h right here. You see h right here is mean the partial derivative, and you will get the result, the matrix right here, and this matrix next we use to update covariant. Remember that, okay? So summarily, we have filters. We compare the standard common filter and the standard common filter. What is different right here? In the state prediction, right now we don't use linear motion. We use the function right here. Look, remember it's non-linear motion, right? And measurement FS, and we have the measurement update right here. We use the S right here. It's not the matrix function matrix right here. We don't have this one. We have to linearly approximation to derive the h right here, and we plug it in, put it back into the formation and formula. We got the stable update covariant update. So differently, in the standard common filter, we already have the app right here. We got the S right here. It's easy for us to get the result, but the non-linear motion, we have one more step to calculate because there's a to update, to get the covariant update, we have to use the Jacobian to calculate the measurement matrix, right? So summary, so the common filter cannot use when the measurement or the state remember when the measurement or the state transition function is non-linear, right? Remember that, because this would result in non-Gaussian distribution, right? And we take the linear approximation to use this approximation to update the covariant of this estimate, right? This linear approximation makes you the first two term of the Taylor series, right? So will give you another example. You already understand this one, right? Because the measurement update right here is not the same, so we don't know the measurement matrix. So we have to use the because the different coordinate, one is the polar coordinate and the other Cartesian coordinate, how to get relationship between them. We have the formula right here. Remember into the math calculatory. I think you know about this formula. And right now we can use formula. We use this one. We use the s. This is the function, right? So and we use the Jacobian to get the measurement matrix right here, and after that we apply to the Kalman filter to get the S and P. So standard Kalman filter is required to calculate Jacobian of the nonlinear function as a part of every single iteration, right? Remember that. So I show you another example right here to familiar with the standard Kalman filter. The motion is constrained because we have the drawn right here. Its motion is constrained by y-axis, and the state variable right here is okay. The overall angle, the velocity, and the position right here. So this drone would like to know the distance between the X and the world. So important measurement to help if the drone would like to travel inside the room, outside the building, or while maintaining the safe distance from the world. Y right here. So you have the Y right here. So and the safe distance from the world to drone. Okay, and look at this. We can guess the distance right, the function of the right here. Apply the basic trigonometry. We can determine the measurement model. The measurement model of the drone. Okay, it means the world minus I. This is nonlinear function, right? So we have to use the standard Kalman filter to show for our estimation, right? You have to linearize the function. So to do that, you remember we apply the standard Kalman filter, and we need to calculate the h. The Jacobian of the measurement model are defined above. So we have to do partial derivative. Okay, and when we derivative, we will get the result, the measurement matrix right here. And from here, you can calculate in the covariant update. Quickly help you to do that. So, standard Kalman filter equation. Summary, we have the formula right here. The matrix in the blue right here, whereas the Jacobian is U. Okay, if another state transition and measurement function is non-linear, remember if state transition or measurement function is non-linear, we have to apply the Jacobian. So that's about the standard Kalman filter. difference for extended Kalman filter is applied for the nonlinear function, right? Nonlinear motion, and we use the Jacobian to calculation measurement matrix for update covariant, right? That's the differences between the standard Kalman filter and the standard Kalman filter right here. Okay, I hope you have the basically understand the extended Kalman filter. We will talk this one next video about the tracking the Kalman filter, tracking the object, right? Autonomous vehicle tracking the object on the road. For example, the pedestrian on the road, how we predict the state of the pedestrian on the road. Okay, bye.